Okay, so it is my great pleasure to welcome Dr. Paloma Huidobro today. So Paloma is a researcher at the Institute of Telecomunications in Lisbon. And today she's going to discuss space-time metamaterials, dragging and amplifying light. Paloma, please.
Thank you. Thank you, Sebastian. And also thank you to you and all the organizers for inviting me to give this seminar today. I would like to start by thanking the people that I have worked with in this in this work, who are Emanuele Galifi and John Pendry from Imperial College London, and Mario Silveriña from Lisbon, who contributed to the topic that I will speak about in the first part of the talk. Okay. So considering media that vary not only in space, but also in time, allows to go beyond the properties of conventional metamaterials. And the reason behind this is that temporal variations break energy conservation and reciprocity. And this allows to overcome fundamental limits posed by purely spatial metamaterials. And this is actually being explored across the whole spectrum of metamaterials, with examples in acoustics, where you can actually get media in motion at sufficiently large speeds or frequencies. In mechanics, for instance, you can get gyroscopes to rotate. And in electromagnetics, which is my main field of interest, at low frequencies, it is possible to control circuit elements by electronic means and achieve temporal functionalities also. And more recently, it has even been possible to achieve strong and efficient modulations in electromagnetism, even at high frequencies, which I think it's very interesting because this will allow for exploring new possibilities in the tailoring of light-matter interactions, even at the quantum level. And there are two reasons why this has been made possible. Two main reasons why this is now possible. The first of them is the use of new materials. An example of this is indium tin oxide, which is an epsilon near zero medium. And what is special about it is that the fact that the permittivity approaches zero at the plasma frequency, which occurs in the near infrared. So at reasonably high frequencies in this medium, in this material, what the effect this has is that it enhances the intrinsic nonlinearities of the medium by orders of magnitude. So it is possible to achieve modulations of the refractive index that are even of order unity, and you can do this sufficiently fast and at sufficiently high frequencies. On the other hand, there have also been many advances in time modulation schemes using metasurfaces. An example could be the electrostatic modulation of graphene or other two-dimensional materials, which has come about mainly because these materials, being ultra flat, they have lower carrier density, so it is not as difficult. They are not as difficult to modulate, even through a simple electrical gating, as bulky media. So this has enabled a plethora of ways of modulating electromagnetic metamaterials and metasurfaces, and there is now a great interest in time-modulated metamaterials across the whole realm of the metamaterials spectrum. So we've seen that these temporal modulations can be realized, but why are they interesting? Okay, so the first key aspect of temporal modulations is that frequencies are not conserved when the properties of a medium vary in time. And this can be seen by comparing the way a wave behaves when it encounters a spatial jump with the temporal counterpart when a wave encounters a temporal jump. No? So in the first case, there is a spatial symmetry breaking and the momentum conservation is violated. And we are all familiar with the scattering of a wave onto an interface between two different media, for instance, where the momentum, that is the wavelength of the waves is not conserved, but frequency is. And conversely, when one has a temporal jump, there is temporal symmetry breaking, which violates energy conservation. So the incoming and outgoing waves will not have the same frequencies, but momentum is conserved. In fact, the fact that frequencies are not conserved enable actually new possibilities and examples. Many examples have been shown. I put here a few of them. One of them is time reversal of waves, which can be done by coupling to negative frequencies. And this was shown by the group of Matthias Fink, for instance, through an instantaneous jump and instantaneous time modulation. It has also been possible to show adiabatic frequency conversion in optics using this indium time oxide material that I mentioned through the time refraction at a temporal boundary. And it is also possible to show gain through the conventional method, conventional process of parametric amplification. Another aspect that we proposed is that it is possible to also couple to surface waves in an unstructured surface using only temporal modulations. So, and then this is what we called a dynamical version of the Wood anomaly. So, as you know, surface waves have a dispersion relation that is beyond the light line, so they cannot be accessed directly by propagating waves. And the conventional way to excite a surface mode is usually by structuring the surface with a periodic spatial grating, which gives a momentum kick that is enough for a propagating wave to excite an evanescent mode, the surface mode. So what we proposed is to do the converse situation, to impose a periodic temporal modulation, so a temporal grating without any spatial structuring of the surface, such that it can give the extra frequency, the frequency mismatch that there is between a propagating wave and the surface mode. And we suggested that this could be done with graphene that can currently be modulated fast and efficiently enough. And here you can see two videos of what happens without and with the modulation when there is a pump or a wave coming into a graphene layer. You see that without the modulation, there is a part of the radiation is transmitted, part of it is reflected by the graphene. And with the modulation, you see that there is a wave that is a surface wave that is left behind, which would be a surface plasmon in the case of the graphene. Okay, so after this, another key aspect of temporal modulations is the possibility of breaking Lorentz reciprocity and achieving asymmetric an asymmetry in the wave propagation in the forward and backward directions. This is actually something that is sometimes not very easy to realize, but is essential to some technologies as it enables the possibility to realize devices such as isolators, circulators, and so on. And in particular, in electromagnetics, the conventional approaches to non-reciprocity are sometimes not very practical. Usually at low frequencies, high magnetic fields and magnetoelectric materials are employed, but this is not easy to scale to higher frequencies or to smaller sizes. So alternatives have been proposed. One has been the use of nonlinearities, but this also has some limitations. So motion or the synthetic motion that can arise together with temporal modulations has been proposed as a viable alternative. So space-time modulations, so modulations that are not only temporal but are coupled between space and time, actually allow to break reciprocity because they impose a directional bias. And examples of how this has been employed are, for instance, the realization of isolation or topological phases in acoustics, the asymmetric diffusion of charge carriers, but probably the most well-studied system is that of a traveling wave modulation. So in this system, the parameters are varied such that the modulation appears to drift along one direction, but there is actually no matter in motion. And this could be realized with an electromagnetic metamaterial, for instance, by varying permittivity and permeability with the schemes that I have discussed previously, or it has also been realized for other systems, for other metamaterial systems. And this has actually been looked at by many groups from the different spectrum of metamaterials. And it is the topic of the main part of today's talk. Okay, so let us try to understand a little bit more how these media behave. And for this, let me look at some dispersion diagrams. So here I'm showing the dispersion diagram of a spatial grating. So this is a grating with a periodic modulation of one parameter. Here I'm choosing the permittivity, for instance, so it is made to vary periodically along one direction. And the dispersion diagram corresponding to this is the usual one that we are all familiar with, which shows frequency band gaps. On the other hand, a temporal grating where a parameter is made to vary in time periodically shows vertical K-gaps. And the reason for this is that in this case, the reciprocal lattice vector of this grating lies along the frequency axis. So it mixes bands that come from the negative frequency part with the positive frequency part. And this gives rise to these curious band gaps that are unstable because they host complex frequency states. And this is actually the realm of parametric amplification, which occurs when a medium is modulated or is made to vary at twice the operating frequency. So now, how do the dispersion diagrams of traveling wave modulations look like? So as I said, now I consider a traveling wave modulation where the space and time variables are linked together, and the parameter, the relevant parameter, varies in space and time, so that in space it appears to be drifting with some velocity. So we have two regimes in this case. One is the first one is the subluminal one. So in this case, the velocity of the grating is smaller than the velocity of waves in the medium. And what happens is that the reciprocal lattice vector is now tilted. It is not horizontal or vertical, but tilted, because it has some spatial and some temporal component. And this results in dispersion diagrams that are asymmetric with respect to the two axes in this plot. And in turn, it results in asymmetric band gaps that have been exploited for non-reciprocity. Mainly, so basically because while a forward propagating wave is blocked, a backward propagating one is not blocked. No? So you can achieve this kind of effects. And then there is a second regime where the modulation is superluminal. And this is possible because there really is no matter in motion. This is just a modulation. So it is possible to design a grating that moves faster than the speed of waves in the medium, or the speed of light in vacuum in our case. And this results in band gaps that are also asymmetric and that are of the temporal kind. So they are K gaps and they are unstable. Okay, so but now we ask the question if it is possible to realize other non-reciprocal effects rather than these non-reciprocal band gaps that have been well studied in the past. And the answer is that yes, it is possible, and this non-reciprocity actually emerges in two situations where we can find analogies between synthetically moving media, so this is space-time metamaterials, and matter in motion. Okay, so the first effect that, or one effect that emerges when matter is in motion is the Fresnel-Fizeau effect, which is the dragging of light by a moving medium. So this was first measured by Fizeau in an experiment that he set up, where he was able to demonstrate that as measured from a lab frame, light that propagates through moving mediums, for instance, in this case, it was moving water, travels at a different speed that that light that propagates against this moving medium. And the reason for this is that moving matter drags light. So we asked the question if it was possible to realize light dragging with our space-time metamaterials, and the answer is yes, that that in fact, in some particular cases, it can be shown that at very low frequencies, this is what indeed happens. Then the second effect is that moving matter radiates. And this is, for instance, the case of free electron lasers or of traveling wave tubes, where electrons in motion are used to radiate. And we will see that this can also happen in space-time metamaterials under some particular circumstances. So we will see that we will find light amplification based on a totally different mechanism from parametric amplification. So in the rest of the talk, I will speak about these two topics. So let me go first into the dragging of light by synthetic motion. Okay, so here we are interested in looking at the response of space-time metamaterials at long wavelengths and at low frequencies. So for this purpose, we used homogenization theory. So we start by considering a space-time modulation of the electromagnetic parameters that can be the permittivity, the permeability, or one of them. And we assume that the medium is initially isotropic, it is non-dispersive, and it is linear. Next, we make a transformation to a frame that commoves with the modulation, and we make actually a Galilean transformation. And we arrive at Maxwell's equation plus a new set of constitutive equations, which show a magnetoelectric coupling similar to the one that appears in moving media. But now this has an interesting property, which is that while the original parameters depending on the spatial coordinate and the temporal coordinate, these ones depend only on the spatial coordinate in the comoving frame. So this means that we can actually apply the conventional approach of homogenization, but in this frame. So this is what we do. We homogenize the parameter in the comoving frame. So we assume, as I said, that we are at long wavelengths compared to the length scale of the spatial modulation, and that we are at low frequencies compared to the modulation frequency. And we use the conventional homogenization approach, which for the parallel components means to carry out these integrals, where now the permittivity and the permeability are evaluated in the comoving frame. For the perpendicular components, we need to carry out similar integrals. But now we see that in the comoving frame, they have the permittivity, permeability, and the magnetoelectric coupling. They have achieved a slightly more complicated form that depends on all the parameters, that depends on both epsilon and mu, and on the velocity of the modulation. And what we see is that if the velocity is 0, so if there is no space-time modulation, then these, the perpendicular components of epsilon and mu reduce to the same as the parallel components. So we retrieve the usual homogenization equations for isotropic media, and the magnetoelectric coupling goes away, as expected. So now we have formula that allow us to homogenize the space-time parameters by moving to a moving frame, but we have to go back to the lab frame. So we do that again by undoing the Galilean transformation, and we arrive at this set of constitutive parameters that again shows a magnetoelectric coupling, and where the parameters are given by this formula here. So, but the thing to notice is that in the effective parameters of the spacetime medium are uniaxial. So initially we started with an isotropic medium, but because the modulation gives a preferential direction, the effective parameters are now uniaxial, and they show a moving medium type coupling with this bianisotropic term. If the modulation speed is 0, then we recover the usual homogenization formula. And something curious to note is that any synthetic motion yields bianisotropy already in the co-moving frame, which is in contrast to what happens with moving media, which are isotropic in the frame that co-moves with the modulation. And finally, what happens if only one parameter is modulated? Well, the effective parameters in the co-moving frame will not have some value that can be extracted from this formula, but it's non-zero. But it turns out that transforming back to the lab frame, all the homogenization integrals cancel out, and we end up with an bianisotropic coupling that is 0. And this is something that we will see the effect of this when I show in the results later on. But now let me show you that in fact it turns out that the formula that I showed for homogenization are exact if we assume there is no backscattering. So we consider impedance matched media. So epsilon and mu are proportional at all points of space and time. And in this case, as you know, forward and backward waves decouple, and we end up with Maxwell's equations reduced to this single equation, which we can transform to the co-moving frame. We define a local wave speed that depends on the spatial coordinate in the co-moving frame, and we can find an analytical solution for the field where we can infer a wave number as given from this expression that I show here. And it turns out that if we use this wave number through a dispersion relation to infer the permittivity, permeability, and the anisotropic coupling of this medium, we recover the same formula that we derived with homogenization. So this means that homogenization is actually exact if there is no backscattering, and that we have an exact formalism for this case. And we also see something to notice in this formula, which is that the field depends on the solution of this integral here, and which has some singularities when the local speed of waves equals the modulation speed. And what this tells us is that the block modes picture and the homogenization picture is valid for as long as the modulation speed is larger than the range of variation of the local speed of the waves imposed by the grating. Otherwise, what this formula tells us is that the wave number becomes imaginary and we see field amplification. So this is a regime where that cannot be described by homogenization, and that I will not go into in the first part of the talk. So to summarize a little bit the theory that I have introduced, we are working with homogenization in the co-moving frame and transforming back to the lab frame to get effective parameters. And these formula are actually exact in the absence of backscattering, which happens at any frequency if the medium is impedance matched, or in general, if there is no impedance matching. It happens when we are far enough from the band gaps, and the backscattering can be neglected as a good approximation, which is at low frequencies or at low modulation speeds, low subluminal modulations or high superluminal modulations. So gratings that are close to being only spatial or only temporal. And now we can apply our formalism to any traveling wave, to any traveling type modulation, which could be a stratified medium, or the traveling wave sinusoidal modulation that I discussed. And this is where I will focus. Okay, so let us now look at some results for the sinusoidal modulations. So I'm looking at a space-time metamaterial where epsilon and mu vary following these cosinusoidal forms, with some amplitudes given by these alphas. So this is how epsilon and mu look in one period in the comoving frame. And this is the shape of the local wave velocity that is associated to this refractive index modulation. And the first thing to identify is where the region where homogenization is not valid is. And this is, as I said earlier, precisely within the maximum and minimum value of the local wave speed. So for any grating speed that is within this maximum and minimum value, I will not be able to apply homogenization. In the particular case where the modulation speed equals the modulation of waves in the grating, I would be in the so-called luminal case that I will discuss later. Okay, so let's look at what effective medium parameters we get by applying our formalism for a case where there is impedance matching. So we have also exact solutions. And here I'm showing the effective epsilon and mu and the magnetoelectric coupling as a function of the modulation speed. And the first thing to notice is that there is a gray area that I am excluding because it corresponds to this area. So there is no homogenization here. The second thing to notice is that the effective parameters start when the modulation speed is 0. They start at the background value for the permittivity and permeability, and they start at 0 for the magnetoelectric coupling. And as the velocity increases, the velocity of the modulation increases, the effective epsilon, mu, and chi increase, and they don't increase without bound. They increase until they reach a saturation value. This can be seen here more clearly in the inset, where I'm also comparing the result of solving the problem by using a Fourier-Floquet expansion, so a spatiotemporal mode expansion, and taking the approximation of considering only the first few modes. And it is clear that this approximation doesn't work in this limit because it enters into this so-called luminal regime, which is a completely different regime that we cannot treat with this approach. And then as we overcome this regime, we enter into a region where the parameters become lower than the background medium for epsilon and mu, and lower from 0 for the magnetoelectric coupling. And as the velocity increases for superluminal speeds up to the point where the modulation is purely temporal, they tend asymptotically to the background values for epsilon and mu, and to 0 for the magnetoelectric coupling. So there is only magnetoelectric coupling when we have really a space-time modulation, when we are not only spatial or only temporal. And in fact, this threshold, this saturation here has physical implications, and because they separate a regime where there is localization of pulses of light, the luminal regime, and a regime where we can see oscillations. This is something that we have looked at a different work, and I don't have much time to go on it today. So next, from the effective parameters, we can look at the effective wave velocity. And correspondingly from these parameters, we get that for subluminal speeds, the mode velocity of the forward wave, the wave that co-propagates with the modulation, decreases from the background value for subluminal speeds, and then it increases from a saturation value for superluminal speeds at the luminal limit, and then decreases again back to the background value. And if we can see in these sketches how this the effect that this has in the dispersion relations. So we see, and we can see that it is opposite for subluminal and superluminal modulations, as in the first case, the speed is reduced for the forward wave, and in the second one, the speed is increased for superluminal, for forward wave, sorry. In the meantime, the backward wave is very little, is affected very little by all of this. You can see the effective velocity of the forward wave in this inset, which changes very, very little. And the reason behind this is that this is completely non-reciprocal. So forward waves are strongly affected by the modulation, while backward waves barely notice anything. So, and this non-reciprocity is reflected in these band diagrams, which are asymmetric. So we have achieved non-symmetric band diagrams without relying on any band gap physics, so very far away from the band gaps. So now, what happens if the modulations are out of phase? Because here I considered the case. I remind you where the modulations were matched. So epsilon was basically equal to mu or proportional to mu. So in order to see the effect of out of phase modulation, I'm showing this plot where I show as a function of the modulation speed, so the same as before. I show a contour plot of the effective magnetoelectric coupling for different phases of the modulation that are encoded in this diagram. So phi is the angle between the electrical and magnetic modulation in this phase diagram, such that, for instance, phi equal to 0 corresponds to only electrical, pi over 2 corresponds to only magnetic, and so on and so forth. So the first thing to consider is that we need to exclude the regime that I mentioned previously a few times, which is given by this, which is given when the modulation speed is between the minimum and maximum local wave speeds in the co-moving frame. And it turns out that this gives this shape that is highlighted in gray, because it is maximum when the modulation is matched, but it is minimum. It almost vanishes. It vanishes actually to order alpha squared, alpha being the strength of the modulation, when the modulation is anti-matched, because in this case the refractive index is practically constant, and the local speed of waves is practically constant. Okay, so let us first start with the case that I showed in the previous slide, which is modulations that are in phase. So this corresponds to these lines here, and what we see is what we saw in the last slide. So at low subluminal speeds, the effective magnetoelectric coupling increases from 0 to up to some value, and then for superluminal speeds, it decreases from some value, from some negative value up to 0. And this results in these two dispersion relations that I showed. Now, what happens when they are in antiphase? Well, we see that the sign of the magnetoelectric coupling has changed. So now it is negative for subluminal speeds and positive for superluminal speeds, but it has overall the same behavior of increasing towards the threshold, towards the luminal speed. However, the band diagrams are now bended in the opposite direction as before. And finally, when there is modulation of only one of the parameters, you see that the effective magnetoelectric coupling is 0, as I had anticipated earlier on when I explained our homogenization theory. So the effective magnetoelectric coupling is 0 if we modulate only one of the parameters, and in this case, the dispersion relations are completely symmetrical. So there is non-reciprocity only if we modulate epsilon and both epsilon and mu, and the direction of this non-reciprocity can be tuned by choosing the phase between epsilon and mu. So compare this case with this other case. and also by choosing between subluminal and superluminal speeds. So far I've been looking at waves that propagate in the same direction as the modulation. So let us look now at off-normal incidence. So now I'm plotting here lines of contours, so contours of constant frequency as a function of kx, the momentum along the propagation, and ky, the momentum perpendicular to it. And it is clear that the dispersion curves are displaced from the usual cones that are shown in gray. And it is clear that the direction of the displacement is opposite for subluminal and superluminal speeds, even if the modulation travels in the same direction in both cases. So this is where we make our analogy to the Fresnel drag of light, which, as I mentioned earlier, it was measured by Fitzhugh with light propagating along flowing water, and which can be actually explained by the velocity addition formula of special relativity. So a light that moves along with a flowing medium will show a velocity measured in the lab frame as the addition of the velocities, and light that propagates opposite will be seen as propagating with the subtraction of the velocities. So we can conclude that synthetic motion yields a light drag when both epsilon and mu are modulated, and that this light drag is tunable. Okay, so let me now go to the second part of the talk, with I speak about this light amplification. Okay, so now I will be talking about the regime that I was avoiding in the previous part of the talk. So this is what we call the luminal regime. So we can see some of the effects by looking at the band diagrams again, and looking at what happens as we go from a subluminal modulation to a superluminal one. And we notice that there is a point when the modulation speed, when the modulation speed equals the modulation of the waves in the medium, that the reciprocal lattice vector is actually aligned with the bands. And what this means is that all the forward waves will be degenerate along this line, while backward waves are barely affected, are basically not affected. So this is a completely different regime where the physics cannot be described using Bloch modes, and this is the reason why homogenization was failing here. And in the past, it was also identified as producing a non-convergent Bloch expansion. So if you try to design a space-time expansion, mode expansion of the modes, you will see that it doesn't converge when the modulation speed is between this range. That happens to be exactly the same range that I identified with homogenization earlier, which is the maximum and minimum local wave velocities imposed by the grating. Okay, but we can still go back to the theory up to the point where I say that I would not apply it to this range. We had arrived to this to a solution for the field in the general case, and what I said is that if we are precisely in this range of velocities, this factor here becomes imaginary. So there is exponential increase, there is exponential growth in the field. So in this case, it makes more sense to look at the change in energy in the synthetic motion, along the synthetic motion. And it is possible to write down an equation for the energy, for the rate of variation of energy, that tells us that energy increases when there is a positive change in the slope of epsilon. And actually, this increase is maximum when the slope is maximum, which in this most simple case, it would be here when the speed of the modulation equals the background speed of the waves. There is another term in the equation that tells us that, that describes how the energy flows from the point where there is maximum increase, in the case if it was not exactly the luminal speed, towards the point of luminal speed. So from this, we see that the radiation is actually trapped at an accumulation point. So this is acting, this point in the grating acts as an accumulation point, and all the radiation will be trapped here and compressed, and it will travel along with the grating. So let us see how this looks in real space. No? So here I will show the results of our analytical formula and the numerical results based on transfer matrix of propagation of an incident wave through a space-time, through a slab of a space-time grating, where I'm varying this time only the permittivity, and which moves at luminal speed. I will plot one temporal period, and I will show different lengths of the slab. So starting at zeros, what we see the constant energy of the input plane wave. Now we start increasing the length of the slab, and we see how the energy starts to build up at this point. If we increase, further and further, we will see how energy is really building up at this accumulation point, which is the point of maximum change in the slope of epsilon. And we can understand this by thinking of the local speed of the waves. So in this area here, the local speed of the waves is larger than the velocity at which the grating moves. So the waves will try to advance compared to the grating. And this is true until they arrive to this point, because at this point, their local speed will be lower than the grating velocity. So here, the grating wins and the waves are left behind. So this is acting as an accumulation point. And conversely, this acts as a repulsion point. So we have gain and we have loss in each period of the grating. So, here we see how light is trapped in the moving grating and how there is exponential amplification and compression at the gain and loss point, respectively. We see that this is fully non-reciprocal. It only works for forward waves. It is completely transparent to backward waves. And maybe most importantly, there are no complex eigenvalues. I don't have band gaps. I'm not working with the non-reciprocal band gaps regime. So I don't have any complex frequency that can account for the gain. So this is a totally different gain mechanism from parametric amplification. It is all due to forward scattering. So then if gain does not come from complex eigenvalues, where is it coming from? And the answer is that it is coming from the compression of lines of force. So this sketch shows an input plane wave into a luminal medium, as the one I showed before, and it shows how the output consists of compressed pulses of pulses, which are built up by the compression of the lines of force. So while in usual media, lines of force are constantly created, in these luminal gratings, in this space-time media, they are not being created. They are only being compressed at one point and decompressed at the other point. So it is just a redistribution of the energy. So, sorry, a redistribution of the lines of force. Energy is being extracted from the motion of the medium. And what is happening also is that as the pulse travels through the grating, through the moving grating, there is coupling to higher and higher frequencies. So this requires, the only requirement that this has is that the medium is dispersionless. Because otherwise, when a higher frequency is excited, then it will have a wave group velocity that is not aligned with the velocity of the grating, so it will jump out of the luminal condition of the luminal regime. So we have proposed that this could be realized in graphene. And the main reason for this is that we can make use of the tunable conductivity of graphene, which has been reported to be strong enough and fast enough for our purposes. Now, the advantage of luminal space-time modulation is that actually we don't need very high modulation frequencies. So we will be working at an operating frequency that is, in fact, higher than the modulation frequency that we will use. And this is done, and the reason for this is that what we want to match is not the frequencies as in parametric amplification, but it is the speed of the modulation and the speed of the waves. Now, we also need a linear dispersion relation. And in general, graphene supports surface plasmons, surface waves, which are inherently dispersive. But it turns out that there is a mode that emerges when a double layer of graphene is considered that has a linear dispersion for a wide range of frequencies. And this is the acoustic plasmon branch in double layer graphene, which has the condition that the distance between the two graphene layers has to be smaller than the decay length of the surface wave away from the graphene sheet. And this is a condition that is currently matched in experiments where they have achieved in the Coppens group distances between two graphene layers as small as 1 nanometer. So we set up a simulation, a transfer matrix-like simulation, where we consider two graphene sheets that are displaced at a nanometric distance, and we assume that their Fermi level varies as our traveling wave modulations. Then, as I said, we work at a frequency that is larger than the modulation frequency actually. And these snapshots show how the graphene plasmon that lives in this double layer graphene gets compressed and amplified at this gain point as temporal periods go by. Now you may notice that at the same time as the compression goes on, the pulse is also getting a little asymmetric, and the reason behind this is dispersion. I mentioned earlier that in order to get this luminal effect, we need to have a dispersionless medium. And the dispersion of the acoustic branch in graphene is very linear up to some point where some nonlinear effects start to emerge. So what is happening here is that we are arriving at that point. So we are starting at some, and this can be seen by looking at the frequency content of the pulse in the frequency K space, which is what is shown here. And you can see how at the frequency content of the pulse increases as the grating propagates along. And at some point, it increases so much that it has the frequency of these components of the plasmon, these frequency components of the plasmon, will have moved away from the linear regime, and they will have a group velocity that is not aligned. It's not within the minimum and the maximum values of this of the wave speed imposed by the grating. So this means that some frequency components are getting behind, which makes the pulse look asymmetric. And if we continue, actually, there will be frequency components that actually fall off the grating as they cannot cope, and this makes the pulse break. So this shows that it may be possible to observe this mechanism of luminal amplification in graphene with graphene plasmons, and that there is some room until dispersion starts to affect the effect. So in conclusion, I have shown you some effects that are possible by temporally varying medium in metamaterials. Something that I have mentioned briefly is the dynamical good anomaly, where we can couple surface waves through time modulation only without the need of structuring a surface. And then I have also discussed two non-reciprocal regimes that emerge in space-time traveling wave modulations that are not the conventional high-frequency, non-reciprocal high-frequency bandgap case. And these are non-reciprocity emerging at long wavelengths in the quasistatic limit when both epsilon and mu are modulating, and which can be which shows an analogy to dragging of light by moving media. And I have also shown the non-reciprocal and broadband light amplification, which occurs in this media at luminal speeds. So when the modulation speed equals the velocity of waves in the medium. So with this, I thank again my collaborators, and I thank you for your attention.
Thank you very much, Paloma, for this very nice review of your recent results on time-modulated metamaterials. So now we welcome any questions from the audience. So young people, more senior